पहले का रोड का है, ठीक है। अभी रोड आ रहा है, ठीक है। काम हम करेंगे। अब दे के गया था तुम लोगों को, हाँ। हम छुट्टी में गया था शादी करने के लिए, रोड तुम लोगों को दे के गया था। रोड में रोड
Please just confirm I am audible. And also please confirm slide is visible or not.
मेरा हेडसेट इतना लंबा वो भी नहीं है, इतना लंबा खूब होंगे तो इतना कम होंगे।
So please confirm just whether I am audible or not. Hello. Hello.
Yes sir, you audible.
Okay, thank you. And slide is visible, please confirm.
Yeah, visible, it is
Question
visible.
number 1 is visible.
Yes.
Okay, we'll start within 5 minutes. Let us wait for maybe few students will join. Then after we'll start.
Sure sir.
So now we'll start. So today is a 4 week. So the first question is, what is the energy thickness for the boundary layer with velocity distribution? Okay, the first question is, what is the energy thickness for the boundary layer? I think I'm facing some network problem. Let me correct it. Yeah, now it is okay. So here velocity distribution is given, small u by capital U equal to y by delta. So you need to find out the energy thickness if this distribution is there. So option A is delta by 6, option B delta by 2, and option C delta by 3 delta by 2, and option D delta by 4. So please everyone need to calculate energy thickness of the given velocity distribution, and you write your answer in the chat box, please everyone. Everyone please try to calculate. So please everyone write your answer in the chat box for the question number first. Okay, Abdul is telling option D is correct, delta by 4. Other student please also try to write your answer in the chat box. I'll wait for another 2 minutes for this question. Okay, we need to understand first what is the formula of the energy thickness. So let me just show you. The formula of the energy thickness is your, let us suppose, energy thickness, if you are represent with delta square, delta star, so it is actually here is a capital U, so you need to put the value of this U by capital U here. So what will, so Y by delta 1 minus Y square by delta square. Okay, here is dy. So now you can calculate very easily. That is Y by delta minus 0 to delta Y cube by delta cube. And this is your dy, here also dy. So like that you can calculate the answer for this. So here your Y square by 2 delta minus your delta by 4 Y4 by 4 delta cube 0 to delta. Here you need to put first your upper limit. Lower limit is 0, so we will not write here, only we will write the upper limit. So if you will write the upper limit, delta square by 2 delta, and lower limit when you will put, that is minus lower limit, so when you will put 0 it will come like that, 0. Similarly here, delta to the power 4 divided by 4 delta cube minus lower limit, when you will put, you will get this. So here delta will cancel out 1, so here delta by 2 minus your delta cube will be cancel out, so you will get delta by 4. So here you can take 4 and this is 2 delta minus delta, so it will come delta by 4. So D option will be correct. Like that you will calculate your energy thickness like that for a given distribution. So remember always, please. So hope everyone got it. So the next problem everyone will try to calculate. So the next problem is question number 2. In turbulent flow, which of the following gives the exact velocity distribution in turbulent flow? So logarithmic distribution, Blase's equation, power law with index varying, and the Prandtl's 1/7 power. Prandtl's 1/7 power. This is the last option. So please try to give your answer in the chat box. Write in the chat box, please, everyone. So for question number 2, please everyone try. It's a very basic question. So as I have discussed in the last, I think in third week or in second week, about that I have discussed already. The velocity distribution in case of laminar as well as in case of turbulent. So today I will also discuss, but please first you need to give your answer. Okay, let me discuss. So in case of laminar, actually the velocity distribution here on the question is asking about turbulent flow velocity distribution. We have two type of, in two cases if I talk about, in case of laminar, in case of turbulent. In case of turbulent, your velocity distribution like that. If I draw, let us suppose this is the pipe flow, and here I want to draw, if this is x direction and this is y. So in case of turbulent, your velocity here is linear near the wall and then after logarithmic. Remember please, then after logarithmic. But in case of laminar, your velocity distribution is like that. Parabolic, remember please. Parabolic kind of thing. Here is, just remember, the logarithmic profile. So your first option will be, that is A option will be correct for this question. Always remember. Another, the kinetic energy correction factor in case of laminar will be greater than compared to your turbulent. Why? Because of we do this, why we need the kinetic energy correction factor? When you will average this graph, when you will this graph, you will convert like this kind of graph, that is the average value. Average means what? Everywhere the same value. When you will average this value, then you need more correction in this graph compared to this, because if you will see here, the logarithmic graph almost from up to far extent, here is everywhere changing the graph, but up to far extent, that is from here to here and here to here, only that much is the graph is your linear varying, almost is same. So that's why you need the less correction factor in case of turbulent. So now we'll move on the next question. Next question is, okay, so what is the ratio of displacement thickness to momentum thickness for a linear velocity distribution over a flat plane? So here you need to calculate the displacement thickness to momentum thickness ratio for a linear velocity distribution over a flat plane. So everyone please try to calculate for question number 3. You have 5 minutes. Please everyone try to calculate. Here the linear velocity distribution means whatever the velocity distribution given in the first question, or that is only, that is a small u by capital U equal to y by delta. This is the variation. So considering this variation, you need to please calculate the ratio between the ratio of displacement thickness to momentum thickness. Okay, let me calculate. So here is given the linear velocity distribution means whatever the initially distribution was there, y by delta. So you need to follow this one only. So first of all, we need to know the formula of displacement thickness. That is your delta as well as momentum thickness is theta. We can represent with this only. So this 0 to delta and your 1 minus, here is 0 to delta 1 minus, that is your del u by capital U minus u by capital U. So this is the formula. You can use this one and you can calculate very easy. So how you will calculate? So it is very easy actually. Here I want to calculate. So your delta is so you need to put formulas. First you need to calculate this one. So 0 delta 1 minus y by delta dy. Here is dy. So when you will integrate, this will give you y 0 to delta minus y square by delta 0 to delta. So delta minus here is delta square by delta. So you will get delta square by 2 actually when you will integrate. So delta minus delta by 2. So you will get delta by 2. How you will calculate the momentum thickness? So you know formula already. 0 into delta 1 minus, not like that. So here is y by delta 1 minus y by delta dy. So here is y by delta dy 0 to delta minus y square by delta dy 0 to delta. So you need to write here. So y square by 2 delta 0 to delta limit, and here also y cube by 3 delta 0 to delta. So when you will calculate, you will get here delta square 1 delta, let me write complete, 2 delta minus here delta cube by 3 delta. Here delta square will be, because when you will multiply this you will get square. So now you can write very easily delta by 2 minus square here will only delta will remain, so delta by 3. So here you will get, if I calculate this one, delta by 2 minus delta by 3, 6. So here 3 delta minus 2 delta, so delta by 6. Now you need to calculate ratio delta by theta. So delta by 2, delta by 6. So delta delta will be cancel out, 6 by 2, you will get 3 answer. So option A will be correct for this question. So you need to calculate like that for each question. That is for such type of question you need to calculate with this procedure. Now we'll move on the next question. Next question is, yes. Next question is, in a boundary layer developed along the flow, the pressure decrease along the downstream. The pressure decrease along the downstream direction. The boundary layer thickness would be tend to decrease along the flow, remain constant, increase rapidly along the flow, increase gradually along the flow, 0.0645 meter. Oh, yeah, this is a no. Here is, I think, mistake in the typing, so this should not be there. Okay, so please for question number 4, everyone try to calculate. Everyone please, for question number 4. If pressure decrease along the downstream direction, then what should be happen with your boundary, that is your boundary layer, whether it will decrease or increase, remain constant, and for question number 4, everyone please try to calculate. Try to actually give the answer. Here is not a calculation any, but you have to think about why, if the pressure decrease, then what should be happen with your boundary layer thickness. So everyone know, please try to first understand why boundary layer developed in the flow, then you can very easily understand. Okay. Ranjit is telling option B will be correct, remain constant. Okay. Okay, let me explain. So before explaining, I want to just tell you the discussion about this. With the decreasing pressure in the direction of flow, that is the negative pressure gradient, means what? The boundary layer tend to reduce in the thickness. Means what? Actually here is given. The change in pressure in the direction of, let us suppose if this direction x and this is y, and the plate is here and water is moving in this direction. So in the x direction, del p by del x is decreasing as your x value is increasing. So here is the condition is given. So what will happen? That is the negative pressure gradient. It means your pressure gradient is reducing. So what will happen? Your boundary layer tends to be reduced in the thickness. Why boundary layer generate? Boundary layer here, all you know, at the surface level, no slip condition. This is the first assumption in the fluid mechanics, or actually practically also we can see. Also I have just shown you the previous in the previous weekend. So no slip condition concept I have already shown you. So here your velocity will be zero at the surface level. Now viscosity also play a major role for your boundary layer formation. So what will happen at the initially your boundary layer will like that, but as you will move in the downward direction, what will happen? The more fluid, that is the more fluid seared, more fluid affected due to the viscosity, more fluid, that is your boundary layer will be increasing, boundary layer will increase like that. So this is the basic principle behind the formation of boundary layer. Why? Because bound your here if you will see the velocity distribution like that, then after constant, here velocity distribution like that, up to that your velocity will be vary, here up to that your velocity will be vary, then go straight like that. So what will happen? Why here is varying up to that much depth, here is also increasing, here is very less, your velocity varying up to very less depth compared to here, because of the your viscosity. Because if just imagine fluid in the layer form, so one layer will try to reduce the another layer, try to reduce the velocity of the another layer. So as we will move from here to here, the mass of the fluid here is more compared, here is more compared to here. So that's why the more mass, that is the more viscosity, that is the more layer of fluid will try to reduce this your velocity. So that's why your velocity, that is the variation in the velocity, that is the this depth is increasing towards the downward direction. But the condition is here, if you will pressure decrease along the downstream, if this condition is there, then what will be happen? Your boundary layer will not increase, boundary layer will be decrease, boundary layer will be, if suppose that from here your pressure is decreasing, so boundary layer will be like that. So this was the question. Now we'll move on the next question. Next question is question number 5. Laminar sublayer is a thin boundary layer formed just adjacent to the boundary in laminar flow, turbulent flow, transition flow, or compressible. That is compressible flow. So please everyone try to give the answer. This is a very basic question, very simple question. So everyone please try to give the answer for question number 5. Laminar sublayer. So please everyone try to attempt the question. If you have gone through all the lectures of fluid mechanics in proper way, very easy to give the answer of this question. Okay. Abdul is telling B in turbulent flow. Okay. Other student, please also try to give your answer. Okay. Simal is also telling option B. Okay. So now I want to discuss about this question. So here actually your answer is your actually both student are correct. Option B will be correct for this question number 5. But now I want to discuss it. Let us suppose is a flat plate and boundary layer is formed like that. Here is the transition phase and then after the turbulent. So as it basically up to here, uh, your boundary layer, laminar boundary layer, then transition, and then after your turbulent. In turbulent, laminar sublayer actually in turbulent you can the laminar sublayer thickness will generate like that. This is the laminar sublayer thickness. So actually the boundary layer thickness is not that much, whatever we have drawn, whatever I have drawn here actually. So, but it is very minimum. I want to just show you. Just please wait few minutes. So I think it may be. How actually the boundary layer thickness look like, I want to just show you. Hope I think visible. So we'll move on the, yes, here you can see very easily. So your boundary layer thickness, just see your boundary layer thickness up to that much only, up to that much only. Here boundary layer thickness you can see not visible. The laminar boundary layer thickness is not visible here. If you will see, the boundary layer thickness is like that, coming, and here is the like that. This is your boundary layer thickness, this much. This much your boundary layer thickness you look like. That is very near to the wall. But for your interpretation point of view, we will draw like that, boundary layer thickness, but not like that. Boundary layer thickness is very minimum, very less. As you can see here, very less compared to the width. If the depth of the flow is that much, even your laminar boundary layer thickness is very less. The portion of the laminar boundary layer thickness is very less compared to your transition phase is very much. If you will see here, the transition phase is very high, and the your laminar is less when you will compare the transition and laminar, and then after turbulent. So as you can see, and here your that is the laminar sublayer, you can think here like that, very less, because this is drawn on a scale, so that's why very thickness is very less, that's why not visible your laminar boundary layer and all. But for conceptualization point of view, actually we draw on large scale, or we draw, that is a zoomed view. Now we'll again come back on the questions. So this is what about your laminar, that is the boundary layer thickness. Just I want to present again question. Yes. So hope you all understand. Now we'll move on the next question. Next question is, yes, this is very easy question, so please everyone try to calculate. What is the momentum thickness for boundary layer with velocity distribution is this? Small u by capital U, y by delta. Very easy question. Everyone please try to calculate, because I have just calculated such type of question 2 times in this actually last 50 minutes. So please everyone try to calculate which option will be correct, whether A delta by 6, B delta by 2, C 3 delta by 2, or D delta by 4. After this question, maybe I'll take 5-minute break. So please everyone try to calculate. Momentum thickness. Okay. Abdul is telling A option. Please, everyone try to calculate. Everyone, please. Please, everyone try to calculate for question number 6. Okay, Simal is telling option A, Ranjit is telling option B. Okay, Anurag is telling option A. I'll wait 1 minute more for maybe another student will give the answer. After that, I'll discuss. Okay, let me discuss. So everyone know the momentum thickness formula, just I have told you. So formula is 0 to delta small u by capital U 1 minus, that is here capital U. So this is a simple formula, and here you need to put the value 0 by delta y by delta 1 minus y by delta dy. Now you need to integrate 0 by delta y by delta dy minus 0 delta 0 to delta y square by delta square dy. That's it. Now when you will integrate, you will get what? Y square by 2 delta 0 to delta minus y cube by 3 delta square 0 to delta. So first you need to put the upper limit. When you will put the upper limit, yes, your option is A, delta by 6, but how we will calculate? When you will put the upper limit, then delta square by 2 delta minus lower limit. When you will put y is equal to 0, then you will get 0. Similarly, in the this second term, so delta cube by 3 delta square minus 0. Now delta by 2 minus delta by 3. So here you will take LCM. 6, 3 delta minus 2 delta, you will get delta by 6. So that's it. So like that you will calculate uh, your all answer. That is the for whatever if you are calculating your displacement thickness, momentum thickness, energy thickness, similar procedure you need to follow. The formula you know already for the your density thickness, that is the your boundary layer thickness. The boundary layer thickness is I think delta, and displacement thickness, actually sorry, the displacement thickness is 0 to delta. The boundary layer thickness is delta, but we are talking about the displacement thickness. So here if I put the delta star, and here if I put the double star, so it will be not confusing. So 1 minus u by capital U dy, for this 0 by delta u by capital U, 1 minus u by u dy, and for this 0 by delta u by capital U, 1 minus u square by, this is a small by capital U square dy. So that's it, like that. So everyone please remember these three formulas. Now we'll move on the next question. Question number 7. So actually this is very question number 7. So I'll take 5-minute break. So please everyone try to calculate. After that I'll discuss. Or if anyone want to take break 5 minutes, you can take. No problem. Okay. So the question number 7 is, let me just read. In laminar boundary layer, we are talking about here the laminar boundary layer. You can just imagine the what I was showing previously, the laminar distance. In laminar boundary layer over a flat plate, what would be the ratio of wall shear stress? What would be the ratio of wall shear stress tau 1 and tau 2 at two sections which lie at distance x1 equal to 4 units and x2 equal to 12 units from the leading edge of the plate? The option A, tau 1 by tau 2 equal to 3. Option B, tau 1 by tau 2 equal to 3 raised to 0.5. Option C, tau 1 by tau 2 is equal to 3 raised to 0.25. And option D, tau 1 by tau 2 is equal to 3 raised to 0.33. So please everyone try to calculate for question number 7. Everyone please try. So you have 5 minutes. After that I'll discuss. Okay. Anurag is telling option B. Good. Other student please also try to calculate. Okay, if anyone have solved, please just write your answer. Okay. So only Anurag is telling option B. Let me just check whether option B is correct or not. So let me just calculate. So here is in laminar boundary layer, you know already the laminar boundary layer is very, the distance of laminar boundary layer is very less than after your that is transition, then turbulent. So in laminar, actually this is your leading edge. So let us just assume this is x direction and this is y direction. So in x direction this and y direction is this. So here two sections, you have two sections, like one section you have here, and another section you have like here. That is from the leading edge, the section 1 and section 2. The distance from the leading edge is for section 1 is 4 and for section 2 is like this distance is 12 and this distance is 4. Now you need to calculate the ratio, that is the wall shear stress, that is the shear stress at the wall in laminar here at the wall. So it, your tau is related, that is directly proportional to your root square of distance. This you need to remember always. Your wall shear stress, that is wall shear stress is directly proportional to 1 by root x. So here we have the two distance. So for tau 1 it will be root x1. For tau 2 it will be 1 by root x2. Okay, so now you need to calculate the ratio. So tau 1 divided by tau 2 is equal to 1 by root x1 divided by 1 by root x1 1 by root x2. So now tau 1 and tau 2 will be root x2 divided by root x1. Means what? The root x means what? X to the power 0.5, or you can say x to the power half. So here x2 by x1 power half means what? That is your 12 by 4 power 0.5 means 3 to the power 0.5. Yes, Anurag is correct. So for option B will be correct for your this question number 7. So ratio of tau 1 and tau 2 will be 3 raised to 0.5. Always remember please. So this is a such type of question you expect in competitive exam also. Now we'll move on the next question. Next question is, always remember relation, always remember your shear stress in case of boundary layer like that, the root x. Now for laminar case, remember always, not for turbulent. Yes. So here is separation of boundary can be prevented by separation of boundary, that is boundary layer. Separation of boundary can be prevented by providing a small divergence in a diffuser, providing a trip wire ring in the laminar region for the flow over sphere. Option C, providing bypass in the slotted wing. Option D, all of the above. Everyone please. So please everyone try to give the answer for question number 8. Separation of boundary can be prevented by. I'll not take much time here for question number 8. So we'll move. Actually, for question number 8, all options are correct. Here you can just read the detailed solution. The separation of boundary can be prevented by providing a small divergence in a diffuser, a tripwire ring in the laminar region for flow over a sphere, by providing bypass in the slotted wing. So all options are correct. These are the way for separation, to prevent the separation of boundary layer. Question number 9 is, a flat with a sharp leading edge is placed along a free stream. Actually, here a flat plate we are talking about. A flat plate with a sharp leading edge is placed along a free stream of fluid flow. Local Reynolds number at 4 cm from leading edge is 10 raised to 5. What is the thickness of the boundary layer? So local Reynolds number is at 4 cm from the leading edge, 10 raised to 5. So what should be the boundary layer thickness at that is from 4 from leading to 4 centimeter. At 4 centimeter, what will be the boundary layer thickness? The question is this. Question number 9. Please everyone try to calculate. You have 5 minutes for this question. Please everyone try to calculate. Okay, please let me just discuss for question number 9. So here actually the question is asking the thickness of boundary layer. You need to calculate the thickness of boundary layer. If a plate is placed in a flow, free stream fluid flow like that. So this is your leading edge, and here is 0. Let us suppose this is your 0, and from here the 4 centimeter in this direction, if this is x direction, 4 centimeter let us assume here, and here your Reynolds number at 4 centimeter is 10 to the power 5. So as you know already, the Reynolds number in case of flat plate, if 10 to the power 5, that is a 10 to the power 5, that is flow is laminar. Okay, so for laminar case, your delta is related with your how it is related with your Reynolds number and x distance. So this is the important. So I think it is 5x divided by Re. Let me just verify the formula. Yes, 5x divided by Re. So like that it is related. So your delta is equal to 5 into x is given 4 centimeter. If your all answer in mm, so you need to multiply with the 10 for mm, and Re is 10 to the power 5 root under. So after calculation you will get 0.63 mm. So this is the thickness. Just you can imagine the 1 mm is, when you will see the scale, that is your 15 centimeter scale, what you have used in your, or you are using for making the any line and all, the 15 centimeter, just you can imagine the 1 mm is just a single line, 1 mm is just single line, and this is almost 0.6 mm. 0.6 mm means almost half of this line. So just you can imagine the what is the thickness of the your this boundary layer, just imagine. So this is what. Now we'll move on the next question. Next question is, so what is actually discussion of this question? Let me just, yes. So Reynolds number is less than 5 into 10 to the power 5, 10 raised to 5, the boundary layer is laminar. If your Reynolds number is, in case of plate, not for pipe, in case of pipe, your Reynolds number is 200, 2000 greater the less than and equal to, then laminar. But in case of plate flow, the flow over plate, Reynolds number for laminar, it should be less than or equal to 5 into 10 to the power 5. Remember please, important. So hope you got it. Now we'll move on the next question. Next question is question number 10. Aging of pipe. Aging of pipe implies which of the following? Decrease in the value of friction factor, increase in absolute roughness linearly with time and hence friction factor, pipe become smoother with time, all of the above. Aging of the pipe. So everyone please try to give the answer of question number 10. Everyone please. Just please think. You have 2-3 minutes for this question. Everyone please think. Please everyone try to give the answer. Very simple question. Aging of pipe. Just please think about the terminology aging of pipe. Then you can very easily using your brain and the basic fundamentals of the fluid or your observation also, your field observation also, you can give the answer of this question very easily. You might have seen such type of cases in your home also. The aging of pipe. As the age of the pipe, that is the age of pipe go, that is let's suppose, okay, D option. Seaman is telling option D. That is all of them, okay. That is the if the let us suppose a pipe is there and over the period of time, that is after a long span of time, that is let's suppose 20 or 50, 20 or 25 years, what should happen with the pipe? Whether decrease in the value of friction factor, increase in the absolute roughness linearly with time and hence friction factor, that is overall the option B is whether your friction factor will increase. Option A, friction factor decrease. Option C, pipe become smooth with time. And option D, all of the above. So here I think let me just discuss, then you can maybe have more clarification. So aging of pipe, as you can see in many places, the as you are aware with the corrosion, as you are all aware with the corrosion, so due to the corrosion your pipe maybe at places, maybe some like that, maybe due to the corrosion at the mouth your pipe may be like that, maybe like that. So what will happen, the roughness will increase throughout the your, that is pipe, throughout your pipe your roughness will be increase. As roughness will be increase, you know the friction factor depend on your pipe roughness, so definitely your friction factor will be increase. That is option B will be not, your pipe will not smooth with time. Or so always remember please, here you just see these two statement is contradictory. One is telling the friction factor will decrease, another option B is telling friction factor will increase. So these two option will not correct, whether this will correct, whether this will correct. You don't think if you are not thinking about option C, so all option you cannot say here. So option B will be correct. Over the period of time, your due to the corrosion, your roughness will be increased, or hence your friction factor will be increased. Always remember. Now we'll move on the next question. Next question, question number 11. When the fluid flow along a solid boundary, more and more fluid get retarded in the vicinity of boundary. This deceleration is due to this deceleration that is the opposite of the acceleration. This deceleration is due to option A, high velocity of fluid, option B, high velocity flow outside the boundary layer, high velocity gradient which exists and near the boundary, option D, all of the above. Which option will be correct for question number 11? So please think on that question number 11 and then you try to give your answer in the chat box. Everyone please try to for question number 11. Option C, okay. Gopal is telling option C, high velocity gradient which exists at and near the boundary, okay. Other student please also try. Please everyone try to give the answer for this question. Question number 11. Just use the basic understanding about your fluid mechanics, then you can very easily give the answer. Whatever you have seen in the NPTEL courses, NPTEL, that is the lecture number, week number 4 videos. So based on your understanding, please try to attempt this question. Question number 11. Everyone, please. So please everyone try to please everyone try to give your answer for question number 11. Okay, let me just discuss about the question number 11. Okay, so here is okay, option C is correct, yes, but how it is correct? So actually when the fluid flow along the solid boundary means what? Let us suppose this is the your solid boundary and fluid is flowing in this direction. So more fluid get retarded means what? That is at the surface your velocity is almost same, but here if velocity is, let's suppose at that level velocity is 2 unit, so 2 meter per second, so here maybe at that level your velocity will be reduces, will be less because of the high velocity gradient. As you know already, the velocity is, in case of turbulent, you know, the gradient is like that at the bed level, that is the near the wall, and then after logarithmic like that. In case of laminar also, here is the high gradient, that is the gradient, and then parabolic, from very beginning parabolic, but here is the high, just you can see. So like that. So always remember, please, option C will be correct for question number 11. So now we'll move on the question number next question. So here you can see the detailed solution. When the fluid flow along a solid boundary, more and more fluid gets retarded in the vicinity of boundary, and this deceleration is due to high velocity gradient which exists at and near the boundary. That is at the boundary and near the boundary also. Okay, so we'll move on the next question, which is last question. Here is the very what we have discussed already. So displacement thickness of the boundary layer is what? Which option will be correct for displacement thickness? I need answer from everyone, please. Everyone, please try to write for question number. Here is question number 12. Everyone, please. Okay, Abdul is telling option A will be correct. Other student, please also try to write. Everyone, please write once. Okay. A and C. Why you are telling C? Okay. Means first choice was okay, okay. The other student, please also try to write. We are talking about here the displacement thickness. And what is displacement thickness? I'll just a little bit I'll tell you the concept behind the displacement thickness. But first I want answer from your side. That is, everyone please write which option will be correct, A, B, C, D. I'll wait 2-3 minutes. Just think and write. Okay. Momik is telling option C. Okay, good. Anurag is also telling option C. Simal is also telling option C. Okay. So everyone please write. So actually we have discussed lot about your displacement thickness, momentum thickness, as well as actually problem based on these formulas, displacement thickness, momentum thickness, and energy thickness. Also we have discussed about your how in laminar boundary layer, how your wall shear stress related with the distance, that is the inversely proportional to the square root of the distance. And also we have discussed about your some basic principle of the boundary layers. Okay, Bhavesh is also telling option C. Okay. Okay, just let me just discuss about the formula and then after the concept behind your displacement thickness. Very, very important concept. So formula you all know, the displacement thickness is, if I represent with a star, so 1 minus, that is 0 to delta 1 minus u by capital U dy, and your momentum thickness 0 to delta u by capital U 1 minus dy, and your energy thickness is 0 to delta small u by capital U 1 minus small u by capital U dy. Here is square. So this is the relation between your, that is, this is the formula for all three. Now what is displacement thickness? Actually I want to discuss. So displacement thickness is nothing. So for this obviously your option C will be correct. So actually let us assume a flat plate. As water is entering, as fluid is entering here, let us suppose I want to draw a, so your boundary layer form like that. Your boundary layer will be formed like that if this is the fluid. But what will happen, your here, as you can say, your boundary layer is increasing. Your boundary layer, here depth is different, here depth is different, here depth is different. Your boundary layer depth is increasing, that is the thickness of the boundary layer is increasing as your x is increasing. This is x direction. So displacement thickness is what? Let us suppose this is your streamline entering, streamline going on the your on flat plate like that. So due to this, your boundary layer formation, your streamline not straight throughout, like your streamline not straight like that. That is, if the thickness of here, the distance between from bed to streamline, this streamline, if let us suppose 1, and here is also 1, here is also 1, this is not happen. What happen? Let me just tell you what will happen. So little bit outward, your boundary layer go little bit outward. Why? Because of the maintain the conservation of mass. Maintain the conservation of mass. And how conservation of mass? I just want to show you. Just I want to tell you. Wait few minutes. Like that. So this is streamline just above your boundary layer. So let us suppose here I want to draw a horizontal line. So if I draw here a horizontal line, then what will, here you will get one, this is the horizontal line, and this is for, this is outward, that is your streamline moving outward. So whatever the distance, whatever the thickness of this, that is the how much your, that is from initial uh, condition to finally your how much your that is just above streamline displaced from your initial position. So if this is, so this is known as the displacement thickness. This value is known as the displacement thickness, always remember. And why it is moving outward? Because of to maintain the conservation of mass. And how conservation of mass, just I'll discuss. Conservation of mass, so this is a very basic concepts and important concept, always remember. Here you can see, as you all know, in the boundary layer, inside the boundary layer, your velocity is, if I write v, if I write here v1 and here v2, so inside the boundary layer your v2 will be less compared to v1, everyone know. So just imagine, here is for high velocity, that is here high velocity, this velocity, all velocity will be same, all velocity will be same, but here is less. Here also, here velocity, here velocity, here velocity will be reduces, but above this your velocity will be same. So here high velocity zone is much, just you can see here high velocity zone is much compared to here. Just imagine, here high velocity is much compared to that location. If I name the location 1 and location 2, here high velocity zone is, that is the, that is zone of high velocity. I want to write here zone of high velocity in 1 is more compared to 2. If you want to, as you know, all know the conservation of mass, what the rate of, that is the mass flow rate should be in and out should be same. Mass flow rate should be in and out will be equal. So what will happen here, if your area is, that is the high velocity zone is less, so what will happen, and here is the low velocity zone is high, so for transporting more, because here you need to transport more mass, here you need to transport more mass, because here you have the more area, so there is no problem, but here you have the, you need to transport because here velocity is less. So if you want to transport, like here is m1 m dot, here you also you need to pass m dot, that is a, let us suppose 10 liter, here also you not want to pass the 10 liter. What will happen, so in within the, within less velocity area you need to pass 10 liters. So what will happen, so your whatever the streamline will be go outward, go outward, go outward, for, that is the for balancing your conservation of mass. So this is the whole concept behind your the streamline outward shifting. The concept behind streamline outward shifting is to maintain the conservation of mass. streamline shift outward, and that shift actually out just outer streamline displacement known as the your displacement thickness. So hope everyone got it. So this is all about your displacement thickness. So okay, so today we'll finish here. So we have learned many things today. So always remember, please, this formula, always remember. You can also see the formula for your displacement, your boundary layer thickness for turbulent. Here we have discussed only for laminar, but you can go through also, you can see the formula for turbulent, as well as we have also learned. Yeah, this is very very important. This concept is very very important, and on you can follow the NPTEL video for the whole derivation how it will come. And also always remember these things. Yes, these three formula is also very very important. That is your displacement thickness, momentum thickness, and energy thickness. Also one thing is very very important, the laminar and turbulent boundary layer distribution, and how this is also very very important, how shear stress varies. So shear stress at the maximum velocity, if this is the maximum velocity, if I am drawing the laminar case, at maximum velocity your shear stress will be 0, and at the walls shear stress will be very very high. So this is the distribution of shear stress. This is also important. So I think that's for today from my side. So thank you all. Now we'll meet again in the next class on next Friday with new questions, week 5. So thank you all. Now please everyone
Thank
can leave. Okay, thank you.
you, sir.
Now everyone can leave.
Okay, sir.
Once you leave, then I'll close the class. Please everyone leave the class. Okay, please everyone leave the class. Okay, thank you all. Now I want to just close the class.